Ah, you must be ready for another check on learning. Frankie. So is Frankie. Frankie, come here. Frankie is ready for some check on learning. All right, here we go. So this is for 8.2, and away we go. Oops, sorry. So how is the graph f of x equals e to the x similar to the graph of an exponential function with a base b? How is it different? So remember, these are the two different graphs, and we can compare them. So how is it similar with a graph of an exponential function with base b is greater than 1? So that means that we are going to have two exponential growth functions. So they're going to be growing. So let's see here. Select all the choices that are the same between the two graphs. So they both have the same y asymptote. So y equals 0. Domain, both of them have the same domain that all values of x are defined in this function. They both have the same range from 0 on up. So no positive numbers, but numbers greater than 0. They both have the same end behavior as x approaches infinity. F of x approaches infinity as x approaches negative infinity. It approaches 0. And they both have the same y-intercept, and they do not have an x-asymptote. So those are all of your similarities between the two. So how is the graph of f of x equals e of x different than the graph of an exponential function of base b greater than 1? So b greater than 1, so that could include e to the x as well. Remember, e is around like 2 point something. I think it was like 2.7 or something like that. The growth rate is different for all values of b not equal to e. I would agree with that. The growth rate is different for all values. I mean, b could equal e, so I don't agree with that. The growth rate is different for all values, and the y-intercept is different. No. The y-intercept would be 1 at all of these values. Remember, that's only going to change if you have a plus or a minus something. Growth rate is different for all values of b equals e. So I would say it makes the growth rates the same, so I wouldn't agree with that one either. Okay, so there's your first one. We can check our answers. There you go. The only one that we didn't agree on, or that we didn't say it was the same, was x-asymptote. And the growth rate is different for all values of b not equal to e. So we're at least on the right track. Identify the reference points and the horizontal asymptote for the graph g of x equals that. So remember, our generic function is, we'll say f of x is equal to a. So instead of b, I'm just going to use e because we know we're using e's. E to the power of x minus h plus k. One thing I can just always remember, I don't know why I can remember that, but formula's in my brain. So find the reference points, enter the exact values in the box, or in the boxes. So we'll need to remember what the reference points are, and I'll pull those up in just a minute. But while we do that, we can figure out all of our different letters. So our A is going to be equal to 3, right there. Our negative h, so h is going to be negative 1 because we've got an x minus h, so in order to make that positive we need a negative number in there. And then our k is going to be equal to negative 8. So we can use these numbers to then find our reference points. but I most certainly do not remember what those reference points are off the top of my head. So let's go back into the textbook and let's find it. Here it is. This is in task 3. Let's see here. You can write the equation using reference points. So I'm going to write those down. So our first reference point is h a plus k. And then our second reference point is h plus 1 a times e plus k. So with that, we can come back here. We can figure out our reference points. So our first reference point, we'll do that in blue. So our h is -1, so we got -1. Our a is 3 plus k is -8. So that would be 3 minus 8. So that's going to be a -1, -5. So that's our first reference point. And it says enter the exact values in the boxes, so that just means they want us to use the e. They don't want us to round it or shove it into our calculator. So we'll do the second reference point in green. So our a is 3. So that's going to be, h plus 1 is 0. So our a is 3, e plus k, our k is -8. So these two are our reference points. So just to double check, here's our correct answers. -1, -5, which is what we got, and then 0, 3e minus 8, which is also what we got. So that's good. We're on the right track. So 0. I'm sorry, that's wrong. -1, -5. And I'm typing these in here so you can kind of see what they would look like as you type them in. 3e minus 8. If you type e into your calculator, typically your calculator is going to immediately go into the exponent because typically e's are used with some kind of exponent. So just be aware of that. If you're just using regular e, you'll have to put a 1 in there if you are using a calculator. But we're not, so we're fine. Find the horizontal asymptote. I love finding the horizontal asymptote. It's k. K is -8. Y equals -8. Done. Too easy. We'll even check that one for you too. -8. So this next one, I left some of this information on the screen because I knew that we were going to need it because you can see that we are going to find the equation for the function shown in the graph. The 2 points are reference points. So we've got these 2 points, we've got an asymptote, so we need to come up with our own function. So I left our generic function up there, and I left our 2 reference points up there because those are the 2 things we're going to need. So let's start off with the easy part, our asymptote right there. Y equals -1. Cool. K equals -1. Done with that part. So then we've got our first reference point, which is this guy right here. So that's what? 0, -1, 1/3. While I'm at it, I'll just add the second reference point down here. 1, -1/3 e minus 1. I got that from right there. So I knew that this one was our first reference point because we have h and we have h plus 1. 0, 0 plus 1. So that's how you can tell which reference point you have unless you have something like h or h minus 1. But our formula is for h plus 1. So here we go. So we've got k equals -1. H is going to be equal to 0. That's because of this guy right there. So then we know that a plus a -1 is equal to a -1 1/3. So that means that a is going to equal a -1/3. And I got that from right there. So then all we need is, that's it. That's all we need. We don't need anything else. Because our base, we already know, is e, so we don't have to worry about that. So now we can write our function using this guy up here. So our g of x is going to be equal to a -1/3 e to the power of x minus h, which is 0. So we can just leave it at x, plus k. Oh wait, we know what k is, which is -1. So we'll erase that little guy there, minus 1. So does that make sense? So you'll notice that this is a mirror image of the growth function. So that would make sense why we have that negative sign there. So I feel like that makes at least enough sense for me to say I think we're good. So let's check our answer. -1/3 e to the x minus 1. There you go. Too easy. Oh no. One-third e. Oh, pushing the e on the keyboard actually works. I didn't think it would. X out of the exponent minus 1. There you go. Last but not least, so it says, suppose the population of a colony of bacteria is modeled by the exponential function, blah, 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 where t is in time in hours. Part A, what is the initial value and what does this mean for this situation? It's actually kind of a good question. It gets you thinking about what's actually happening. So the initial value is when no time has passed. So the initial value is going to be when t equals 0. So when t equals 0, this whole thing right here turns to 1, because you're going to have e raised to the power of 0. Anything raised to the power of 0 is 1, so you have 10,000 times 1, so you've got 10,000. The initial value is 10,000, and it represents the starting bacterial population. So what is the growth rate of the bacterial colony? So this is going to require the use of, this is from last lesson, the exponential decay, or the growth and decay function that we used. So I can already tell you the bacterial population, based on the situation, bacteria tends to grow, so it is probably going to be a growth function. So I'm going to go ahead and write that on the screen. So f of t is equal to a 1 plus r t, and then our growth factor is 1 plus r. I don't know if we'll need that whole thing. I'll have to reread the question. Let's go ahead and figure it out. So what is the growth rate of the bacterial colony per hour? So yeah, so we need to figure out what this is. That's our growth rate. But in order to do that, we need to figure out what this is. And that's where we come into our math equation. So let's see here. We've got the function 10,000 e to the 0.162 t. So we can compare this function to this one over here. We've got our a, which is 10,000, and then our e, or our 1 plus r, is equal to e to this number. So notice how our format here is, this is a number raised to the t power. So that's going to be this number raised to the t power. So we can say e 0.162 equals 1 plus r. So then r is going to be equal to e to the power of this small number minus 1. So from there, we're just going to plug that into our calculator. So here it comes. Let's see, let's get out of that. Clear everything out. So I know it's a little messy on the screen right now, but I'm just plugging that part into my calculator. So notice how on the calculator, our e, I mentioned this earlier, as soon as you push it, it takes you straight into the exponent. So that's pretty typical of calculators because usually e is used in conjunction with a exponent. And then I want to get out of the exponent. Minus 1 equals 0.1758. So r equals 0.17586. They told us to round it, but I don't remember what they told us to round it to, so probably the nearest tenth or something. Enter the correct solution in the box, round your answer to the nearest whole number, but note they have a percent. So this number is not the number they want. They're going to want 18%. So we're going to write 18%. That one I do want to check just to make sure we got that right. 10,000 starting bacteria, about 18%. So again, we're heading in the right direction. I like it. After how many hours will there be more than 1 million bacteria? This is where it gets fun. Enter the correct value in the box, round your answer to the nearest 10. So this is where we're going to use a little bit of our calculator. Hope you know how to use those. Alright, so we need to figure out when it's 1 million, right? So we're going to set our, we're just going to put a y equals 1 million in there. Y equals 1,000, 100,000, million. And then we're going to enter these two formulas and figure out where they cross each other. Again, another way to do this, if you want to do it all in one equation, is just subtract 1 million from this equation down here and then figure out where it crosses the x-axis. Either one works. But they did the... Sorry, that was my dog falling down the stairs. So they did the first way in the book, so we'll keep some consistency. So let's see here, y equals 1 million. Okay. And then We're going to enter this red equation right there. I know it's hard to see, but 1, 2, 3. E to the power of 0.162. That's where our x is going to go. Okay, let's get the stuff off the screen. So that's what we're looking at. I didn't think we'd see anything in our graph. So we're looking at y equals 1,000,000. So when we look at our window, our y maximum probably should be something overly huge. Okay, so we can at least see our horizontal line. Let's see here. And then our x value, x minimum is 0, is probably fine. Our x maximum, it's actually a good question. I don't know, so I'm just going to kind of randomly guess a big-ish number. And let's just start zooming out until we see our blue function. Well, that's strange. Why is it down there? So we'll just zoom in, see if we can't figure out what's going on. Alright, so I'm going to keep playing with the zoom until I find it. I'll come back with you when I actually have something interesting to look at. Alright, so I played with it a little bit. This is what I got. Again, once I started thinking about it, it kind of made sense. If you go over here to your window, like what part of the chunk do you want to see? So I just used the trace function on my exponential curve, and I just kept on going until I found it about 1,000,000, and that was when I found like x equals 71 or somewhere around there, right? So that's when I went to my window. X maximum 100, x minimum 0, and then y minimum is what kind of made, once I started thinking about it, made more sense. We know that it's going to cross at 1,000,000 somewhere, so we don't really need anything below, towards the smaller numbers. So just set these to bigger numbers where you can see it, and then there you have it. So then you can come up here to calculate. You want to figure out where they intersect. That's your first one, that's your second one. Intersection at 71 point, that number, we'll write it on the screen. 71.0674. And then y is 1. That little e there means times 10 to the 9th. So 1,000,000. Go away, calculator. So that means that after about 71 hours, you will have 1,000,000 little chunks of bacteria. Let's make sure that's right. It's not. So they got 28.4. So let's see what I messed up here. Okay. So I'm going to rewrite my equation. E to the 0.162, mine's going to be x, and then 1 million so 100,000. Oh, I think I had too many zeros. Come on, people. Why didn't you tell me that? I wrote 1 million wrong, which means I probably entered 1 million wrong in the calculator. So 1 million should only have 6 zeros after it, as opposed to 9. So again, we're going to use our delete button. 1, 2, 3, 4, 5, 6. Okay, let's play that game again. So we look at our window. Let's see here. Our y maximum is what we really want to change. So our y minimum can stay the same. Let's make this a little bit smaller. So close enough. Calculate. Let's do the intersection. 28.4. Imagine that when you put in a million correctly, you get the right number. So after 28 hours, when you're going to have over 1 million things of bacteria. So sorry about that, but either way, we made it through it. I leave takes like that in there. I don't cut them out all the time, just because I like to see, or I like you to see how sometimes when you make a mistake, how you go check yourself. So checking that work is a very important part of mathematics. So here we go. I will see you in class.